Okay, so in the previous session, we have completed till question number 6. Now I'm going to start question number 7 with all of you. Okay. So, in question number 7, the structural and displayed formula of 3 aromatic compounds A, B, and C are shown. Compare the relative acidities of A, B, and C. Okay. So, when you have to do a comparison between the phenol and the carboxylic acid, remember, carboxylic acid is always more acidic. So, if you see here, this one is a carboxylic acid and this one is a carboxylic acid, right? So, if these two are carboxylic acid, so and here this one is a phenol because OH is directly bonded to benzene ring. So that is for sure that this one is the least basic among these three. So I have put B on the least basic side. Now both are carboxylic acid, but if you see over here, that the carboxylic acid group is actually bonded to a chlorine. The neighboring carbon have a chlorine to it, which is further electron withdrawing. So if it's an electron withdrawing, which makes it more acidic, or we can say that it is most acidic among these three. So I would put a C over here and A over here. Is this understandable to everyone? Yes, if anyone have any doubt, kindly ask. Okay. Now we have to explain the answers. Now, so we can write over here that in C, both C double bond O and chlorine are electron withdrawing in nature. Makes OH bond weakest, and that is the reason that C is the most acidic. Is this clear?
Sir, aren't halogens electron withdrawing?
Yeah, halogens have greater electronegativity, so they withdraw electron. That is the reason that we have discussed in the relative acidities of carboxylic acids. I have shared the notes in the group. So if you go through the carboxylic acid derivatives, you can find it on page number, see, yes, here on page number 7 and on page number 6. There's a discussion of electron withdrawing group attached to a carboxylic acid group, okay? In B, sorry, now in A, there is only C double bond O which withdraws electron makes OH bond weak. Okay. But not as weaker in C. In B, the OH bond is stronger. Yes, you can write the electron, the negative inductive effect as well. Then rest of the two as its, or you may write that as the electron withdrawing effect of benzene is not strong as COO negative. Is this understandable? Yes. Okay. Now part B. Methyl benzene can be made from benzene by an electrophilic substitution reaction. Okay. That is the common reaction. Identify a compound that reacts with benzene to form methyl benzene. Identify the catalyst used. Okay. So if you recall, here we have a benzene and we have to make methyl benzene. So yes, who is going to tell me which compound we will use? Isn't it we react it with chloromethane? Yes, very good. And the catalyst that we use is normally aluminium chloride, AlCl3, and more specifically, you can write anhydrous AlCl3. So methane, because there is a one carbon. Chloromethane and anhydrous aluminium chloride. The first step in the reaction is the generation of methyl electrophile. Write an equation for the reaction that generates electrophile. So if you recall, in the first stage, this chloromethane reacts with aluminium chloride, and this aluminium chloride removes the chlorine to form AlCl4 negative, and as a result, uh, we are left with methyl with a positive ion. So that is your electrophile. Is this clear? Yes.
Yes, sir.
Okay. Now, third part. Describe the mechanism for the reaction between benzene and methyl electrophile. Include all relevant curly arrows and charges. So, remember that the first arrow arises from the pi system and it heads towards the carbon of the methyl. Okay. Then the intermediate is a benzene ring with a semicircle and a positive charge. On the carbon where the CH3 is attached, we would show the hydrogen ion over here as well. And now a curly arrow from the hydrogen bond inside the ring. And then our desired product, methyl benzene and the hydrogen ion. Is this clear to everyone?
Yes, sir.
Okay. Now, next part. Identify a suitable reagent to oxidize methyl benzene to benzoic acid. So there is a one common oxidizing agent. Write an equation for this reaction using atomic oxygen to represent one atom of the oxygen from the oxidizing agent. Yes. What is the reagent?
KMNO4.
KMNO4, but remember, do not write just KMNO4. You have to write along with the medium. Normally, in all of the oxidations of our organic compounds, we always use acidified potassium magnate 7. But in this case, we always use hot alkaline KMNO4. So, hot alkaline potassium manganate 7 is used. And now we have to write the equation. So the benzene containing methyl group is C6H5CH3 plus atomic oxygen. And when it forms benzoic acid, here you have a formula as well. So it is C6H5COOH. So there is a two hydrogens are actually removed from here. So those two hydrogen joins with oxygen to form water, and to balance the oxygen, we would put 3 as a coefficient of atomic oxygen. Is this clear?
Yes, sir.
Yes, sir.
Okay. Now, methyl benzene and benzoic acid are both nitrated with a mixture of concentrated nitric acid and sulfuric acid to give mononitrated product. The structural formula of these two products are this and this respectively. Draw the structure of these two products. So here, if you recall, there are two benzene compounds, one having a methyl group on it and the other one having a carboxylic acid group on it. So if you recall, carboxylic acid is electron withdrawing in nature and methyl is actually electron donating in nature. So in this methyl benzene, the next substitution occur at either 2 or 4. So the formula of the product would be having a nitro group on the second position. And here, because carboxylic acid, this COOH group is actually electron withdrawing in nature. So the substitution occur at position 3 or position 5. So the nitro group would be placed over here. Is this understandable to everyone?
सर दोनों इलेक्ट्रॉन विड्रॉइंग है
No, methyl group is electron donating. If you would see over here, you can find this list here on the third page. If these groups are already attached, then the next substitution would occur at these 3 positions. Okay. And if these groups are attached on the benzene ring, then the next substitution occur at these 3 positions. Okay.
Yes, sir. Thank you.
Now, a reaction scheme is shown in figure 7.2. Okay. In reaction 1, what we are seeing that nitro group is converting into amine group. So, and if you see here, we have a C6H4. So basically, for the reaction 1, it is 1 minute, please. Here we have a nitro group, and here we have a CH3 group, and the product over here is that nitro group is actually converted into amine, and here I have a CH3 group. Okay, now if you see in reaction 2, we are getting NO2 positive and Cl negative. This is the hint. Whenever you are observing NO2 positive, it means a diazonium ion is formed. So now it would be nitrogen, triple bond nitrogen with a positive charge and a chloride ion, and here it is CH3. Now here, instead of this, we got an OH. So it is a phenol having a CH3 on it and di. So it means these two are actually going to react with each other and forming a di. Okay. Now, describe the reagents and conditions to produce this diazonium ion from methyl phenylamine in reaction 2. So if you recall, the reagent would be HCl and NaNO2, because these two react with each other to form HNO2, which is actually going to react with the NH2 group. And temperature must be equal to or less than 10 degrees Celsius. Okay, sorry. So temperature would be equal to or less than 10 degrees Celsius. Is this clear?
Yes.
Okay, now describe how this methyl phenol can be produced from this diazoniamine. So there is nothing to do. We just need to heat it or warm it. On warming, the nitrogen gas liberates, forming a phenol molecule.
सर इसमें वाटर नहीं डालते?
Yes, but actually, we in the equation we usually write water, but the thing is that the whole reaction is taking place in the aqueous solution, so there is already water in it.
Okay, sir.
Okay, yeah, but I think we can write water as well. But the reaction is actually taking place in the aqueous solution. Now, draw the structure of the dimolecule Y formed when diazonium ion or diazonium chloride reacts with this phenol. React together in reaction 4. Describe the conditions for this reaction. Okay. If you recall the conditions are actually the temperature again below 10 degrees Celsius, and we use sodium hydroxide. So when these two combines, so there are two possibilities. First, I'm drawing the structure having a diazonium ion. In this die, the triple bond turns into a double bond. So as the structure for methyl phenol I have drawn, in that structure, if you see the methyl group and the OH group are on the two positions 1 and 4. So in that case, you can attach a benzene this to the phenol on the second position. But if you see over here, there is another possibility that these two, instead of this, these two groups are actually adjacent to each other, because if there is a methyl group and then this substitution occurs, so it can be on fourth position with respect to methyl group, or it can be on a second position. So if it can be on a second position, then here we would get phenylamine on a second carbon, and then on the same second carbon there is this diazonium chloride. So in that same way, here the phenol that would form is actually on the second carbon as well. So in that case, the other possible structure for this would be a methyl group over here. And then this is bonded to a phenol on the 4th position. And we have either here CH3 group. So it can be drawn in both the ways. Okay. Is this clear? Now, we are going to start with question number 8. When answering this question, it should be assumed that together all the hydrogen atoms in a benzene ring result in a single unsplit peak at chemical shift 7.2. So it means that at chemical shift 7.2, all the hydrogens of benzene, right? So if I would mark over here, these H5 in all of these compounds, these are of benzene, because when a group is substituted on the benzene, then there are 5 hydrogens. So these all are showing a peak or a signal at 7.2. Is this understandable? Yes? Okay. The structure of 5 isomeric ketones, P, Q, R, S, and T are given. Okay. Identify all the chiral carbon atoms in the structures above. Label each chiral carbon atom with a steric. Okay. So in which molecule we have a chiral carbon? If I draw a P over here, it have a C double bond O and then C which have a 2CH3. So there is no chiral carbon atom in it. If I draw Q over here, in that Q there is a C double bond O, then CH2, CH2, CH3, again no chiral carbon. If I would draw R, a benzene ring, CH2, C double bond O, CH2, CH3. Again, if you see, no chiral center. In S, a benzene ring, then CH2, CH2, C double bond O, and CH3. No chiral carbon. So it must be T. So CH having a CH3 and C double bond O and CH3. So if you see, basically this carbon is the chiral one. So, and which is this carbon? This carbon is over here. So I would place an steric on this carbon. Is this clear? Yes. Okay. So basically, if you recall, it is at 7.5. So it is the peak of these 5 hydrogens. Now there are 3 peaks. Okay, proton NMR spectrum of one of the 5 isomers of T is shown. So it means there are 3 different environments. There is a triplet, means 2 hydrogens on neighbor carbon. Quadrate means 3 hydrogens on neighbor carbon. And singlet means no hydrogen on neighbor carbon. So now we have to figure out which one can show this one. So what I'm observing from here, isn't it an R? Yes, that's what they are asked. Identify which compound gives this structure. Draw the displayed formula of the compound you have identified. Identify the protons responsible for the peak at chemical shift 3.7, 2.7, and 1. C. If you look on R, I am clearly observing that these three hydrogens have two hydrogens in their neighbor. So it means for these three hydrogens, I'm going to observe a triplet, right? And if you look at for these two hydrogens on their neighbor carbon, there are three hydrogen atoms, which clearly means that this hydrogen is going to show a quadrate. And here these two hydrogens are actually the one on one side of these two hydrogens is a C double bond O, so no hydrogen on the neighbor carbon, and the other side it is attached to a benzene ring carbon, which is also have no hydrogen on it. So for these two hydrogens, I'm going to observe a singlet. So they are asking to draw the displayed formula, right? So a benzene ring, then CH2, C double bond O, CH2, and CH3. Yes, is this clear?
Yes, sir.
Sir, in
And
the above spectrum, we have two singlets. What's the other singlet?
that is of these hydrogens. See, I have already mentioned that is of these hydrogens, that 7.2 that we have already discussed initially, because they have given us that at chemical shift 7.2, you are going to observe a one single peak of these hydrogens that are in the benzene ring.
Okay, sir.
So that is actually the common signal which is going to observe in all PQ, RS, and T, because all have this C6H5 group.
सर पूरे बेंजीन की एक ही रिंग बनती है, मतलब एक ही वो आती है पीक.
No, it sometimes it splits into further signals, but here, see, if you read this first line, that it should be assumed that together all the hydrogen atoms in a benzene ring result in a single unsplit peak at chemical shift 7.2 in a proton NMR spectrum. So here they have already told you that in this case, this single peak at 7.2 is of all the hydrogens collectively.
सही है.
Okay, Muzammil? Okay. Now,
सर
what they are saying that, yes,
सर वो जो ये CH की है जो बेंजीन रिंग के साथ कनेक्टेड है, आपने बोला था इसकी भी एक सिंगलेट है सर, इसकी सिंगलेट कहाँ पर है?
this one,
तो सही सही सही.
this one is the singlet of this CHH, because on one neighbor there is a C double bond O, and on the other neighbor there is a this carbon of a benzene ring which have no hydrogen on it. That's why we are getting the singlet.
ठीक है सर.
And here I have a CH2, and on its neighbor there is a CH3. So this is the peak of these two hydrogens over here, and this is the peak of these three hydrogens over here. And this is the peak of these two hydrogens. So that's what they ask you. On the structure you have drawn, okay, identify the protons responsible for the peaks at sigma 3.7, sigma 2.5, and sigma 1.0 on the structure you have drawn. So you can do one thing, that you can mention the peaks over here. So at 1.0, this is CH3. So you may write 1.0 to all of the hydrogens. Then at 2.5, we have these two hydrogens. So here you mentioned 2.5 and 2.5, and then the next one is at 3.7. So 3.7 over here and 3.7 over here. Is this clear now?
Yes.
Okay, now what they are asking, name the splitting pattern at chemical shift 3.7 and explain why it has this splitting pattern. So we have decided that it's a single peak at 3.7, right? Which means we name this splitting pattern singlet. And why it has this splitting pattern? So the reason is on neighboring carbons, there is no hydrogen. Okay. Now, choose from the letters P, Q, R, S, and T to identify the two compounds that each have a doublet peak in proton NMR spectrum. Okay, so see, for a doublet means that neighbor carbon must have how many hydrogens? Yes?
One.
One hydrogen, right? So let's figure it out. Here we are observing a one hydrogen. And here we are observing a one hydrogen. So it means in these two spectrums, there must be a singlet because these hydrogens are neighbor to some other carbon which have a hydrogen as well. So here I can write P and T. Okay. Now, the compound with only 3 peaks in its proton NMR spectrum. Okay. So which one have a 3 peaks? Let's see. Yes, who can figure it out? If you see over here at the first one, if I will point out here, this and this are going to have a similar peak, same peak, one peak. Then the hydrogen over here is going to show you another peak. And then, as discussed earlier, the hydrogens over here are going to show you one peak. Now the two carbon atoms are left, and on those two carbon atoms, there would be no hydrogen, so there would be no peak. So here on P, I'm getting the 2 peaks, 3 peaks. And that's what they ask. So if you look further here, let's confirm other. One peak, second peak over here, third over here, and fourth over here. So here I'm getting the 4 signals. If you look at the next one, all these are similar one. One,
सर बेंजीन
two,
के अंदर वाले सारे कार्बन
yes, yes,
बेंजीन के अंदर
Safiullah,
वाले सारे कार्बन
can you repeat?
I'm saying सर बेंजीन के अंदर सारे कार्बन सिमिलर क्यों है?
Hydrogens, not carbons, because they have mentioned over here. See, I have just discussed earlier that you have to assume, read this. Okay. Now, in this case, one peak. Okay, these all hydrogens are similar. Then second, and then third. If we look over here, 1, 2, 3, and the fourth one of all the benzenes. So if I comment over here, for this I'm getting 3 signals. For this, I will get 4 signals. 1, 2, 3, 4. 1, 2, 3, 4. For this, I'm again going to get 4 signals. For this, I'm going to get 4 signals. And for this one, 4 signals. So only P is the one which is showing me 3 signals. Is this clear? So I would write P over here. Now, suggest a suitable solvent that should be used for obtaining a spectrum shown in 8.1. Okay. So we all know normally the solvent we use is either CdCl3 mostly. Now, the proton NMR spectrum of compound T is compared in the presence of D2O and in the absence of D2O. Okay. Describe any difference between the two spectra. Explain your answer. So if you recall, D2O is used for OH or NH groups, right? But if you see in any one of those compounds, there is no, there is no H or OH group. Okay, which compound is it? It's a R. Okay, you have to just mention R over here. Okay, so I will write no difference is observed Yes, Taha. No, both can be used. TMS as well, but normally TMS we call it reference. You can use TMS as well and CDCl3 as well. But when we use CDCl3, see over here, for when we use TMS, the thing is that in TMS, you are going to get this signal on a 0 as well, right? But here there is no signal over here, so it means TMS is not used. Okay. No difference is observed. Because no OH or NH group, or instead this reason you can write no hydrogen is exchangeable, which can be easily polarized or which can be easily exchanged. Okay. Now the F part. Below to give complete table 8.1 to below to give the number of peaks in carbon-13 NMR spectrum of each compound. Okay. So let's start marking. If we observe this one is going to be completely different carbon than this one. Then we have this carbon is going to be completely different from the rest of the benzene carbons. These two carbons are exactly the same. And then these two carbons are exactly the same. And this one is completely different. So count how many different carbons we are getting over here. 1, 2, 3, 4, 5, 6. 6, right? Then here if you see, these two carbons are exactly the same. And these two carbons are exactly the same, right? Then this one is a different one. Let me do with this one. Then these two are exactly going to be the same one. And this one is different. Now count. 1, 2, 3, 4, 5. So I'm going to get 5 signals over here. Then the next case. These two are CH3 groups which are attached to benzene rings, so show similar structure. Or their chemical environment must be same. These two have exactly the same one. then these two show same structure behavior, same chemical behavior, and these two as well. Yeah, correct, right. So there are 4 signals would be shown for this compound. Now, the last one. It's a completely symmetrical molecule, right? So these two have exactly same structure, chemical environment. These two have exactly same chemical environment. And these 4 have exactly same or similar chemical environment. So here, there would be 3 signals. Okay, Safiullah. Okay. Now, question number 9. Tyrosine and lysine, they have shown you the structure, are naturally occurring amino acids found in protein. The isoelectric point of lysine is 9.47. So it means at 9.47, it is going to be a neutral one. Below this value, it is going to be the acidic one. And above this value, it is going to be a basic one. Draw the structure of lysine at stated pH in the boxes below. Okay, so if it is 1 minute. If it is going to be a neutral one at pH 9.47, so it would be like this. 1, 2, 3, 4, 5. COO negative. And one of the NH3 would be, one of the NH2 becomes positive and the other one stays the same as NH2. Because at pH 9.47 is its isoelectric point, and isoelectric point is the one where the amino acid have a no net charge. So if I'm getting at a pH higher than this, then it means there are more hydroxide ions. So to neutralize those more hydroxide ions, this structure, which is at 9.47, is going to release its hydrogen. And as a result, this NH3 becomes NH2. And the rest of the structure remains same. At pH 7, there are more hydrogen ions. And as a result, what would happen? That the carboxylate ion part, COO negative part, would actually accept this OH, this hydrogen ion to form an OH at lower pH. So these are the 3 different structures of lysine at 3 different pH.
सर वो लाइसिन एट पीएच 12 पे समझा देंगे.
Yes. Okay. I would try to make it. देखें. At pH 9.47, it is neutral because it's isoelectric point, right? Okay. So it means that it must have a no net charge, and that's why at pH 9.47, I have made a structure where there is no net charge. Okay. But if I'm going at a pH 12, which pH is it? It's an alkaline or a acidic one?
Sir, alkaline.
So alkaline. So it means there must be more hydroxide ions, right?
Yes, sir.
To neutralize those hydroxide ions, the lysine would going to release the hydrogen ion. And that's why this hydrogen ion is released.
सही सर ठीक है सर समझ गया.
No, Arisha, not at pH 7, because see, they have mentioned its isoelectric point. At isoelectric point, its net charge is neutral. Not at pH 7, okay? So whatever,
3 plus नहीं होगा एक
sorry,
NH2NH3 plus नहीं बनेगा
at pH 7.
yes sir.
Oh, yes. At pH 7, actually, it is going to accept the hydrogen ion. So this hydrogen ion is accepted at this site as well. But beside this site, the hydrogen ion is actually going to accept it over here as well. Making it a positive one. Yes. Sorry. So when there are excess hydrogen ions, so hydrogen ions are going to be accepted. And when these hydrogen ions are going to be accepted, this group is also going to accept the hydrogen ion, and this stays the same because it is already NH3 positive. Yeah. Thank you, Halima and Alisha. Yes, you can change it. It doesn't matter. But there is one more thing, Saleha. I think you had asked me about this. Okay, just give me 2 minutes, please.